All right, guys, so let's continue with our exponential functions and exponential equations here. So just recall an exponential equation is something that has a variable in the exponent. So sometimes people get confused and see anything that has an exponent and think that it's exponential. But, for example, this first one, f of x here, negative 2x to the fifth, that's actually just a polynomial, right? That's just a monomial, one term. And the difference is that in an exponential function, the variable needs to be in the exponent. So these other two, these are actual exponential functions because you notice in the exponent is where the variable is located. But again, this first one, the variable was not part of the exponent. So just watch out for those. There's obviously different methods for solving equations and graphing and all that stuff. All right, so let's take a look to solve exponential equations, again, where the variable's in the exponent. Sometimes you can use this little property here called, it's like a one-to-one property, and basically what it says is if b is a positive number, so b for the base, and it's any other number than 1, then if b to the x equals b to the y, that means that x equals y. So in other words, if the bases are equal, and then you have an equation, okay, and both sides have the same base, the only way that's possible is if the exponents are equal. Okay, and again, this doesn't apply if the base is 1, because 1 to any power is just going to be 1. So we can use this rule in any other case. So if we take a look, we have an example here. 3 to the 3x power equals 27, and we are trying to solve for x. So with this problem, we want to see if we can write both sides to have the same base. So that we can use this property here. So again, if we notice the left side has a base of 3, we don't really need to change that because we know that 27 can be written, 27 is equal to 3 to the third power. And I chose 3 as a base because that was the base on the other side. So we have this equation, 3 to the 3x must equal 3 to the third. So what that means is that since the bases are both equal, right, if we take a look, that base and that base are equal, then that means the only way that's true is if these exponents also equal each other. So now we can just set up a little equation using the exponents being equal. I know that 3x has to equal 3, and that I can solve by just dividing both sides by 3, and x will need to equal 1. All right, let's take a look at another example here. So we have 4 to some power, 4 to the 9n minus 2 equals 256. Okay, so we got to ask ourselves, is there a way to rewrite 256 so that it has the same base as the left side of the equation? Okay, so 4 to the 9n minus 2 equals, is 256 4 to some power? So sometimes you just have to like guess and check and try things like 4 to the third, 4 to the fourth. And actually you'll find out that 4 to the fourth actually is 256. Okay, so what I did, I just rewrote the 256. Now both sides have the same base, okay, so I can just set these exponents equal to each other now. 9n minus 2 needs to equal 4, and we can of course solve that for n, add 2 to both sides, divide by 9, okay, and we can reduce and get the simplest form. So in this case, n would equal 2/3. Okay, let's try another one here. 3 to the 5x equals 9 to the 2x minus 1. Okay, so this one, they both actually have exponents. Okay, but the trick is still recognize that 3 and 9 can be written with a base of 3, right? 9 is really 3 squared. So for this one, what we can do, I'm going to leave the 3 to the 5x alone. And I'm going to rewrite 9. 9 is 3 squared. And then that's still to the 2x minus 1 power. Okay, so again, I just kind of used the power of 3 to rewrite 9 so that it has the same base. And now what we're going to do, we can use a power, or a property of exponents, I should say, that states if you have something to a power to another power, the properties or the rules of exponents say you can multiply those exponents. So this would end up being 3 to the 2 times 2x minus 1 power. Okay, remember those old properties of exponents. So 3 to the 5x, if we simplify this, 2 times 2x minus 1 is going to become 4x minus 2. All right, and now I have both sides of the equation have a base of 3. So that means that if these things are equal, then their exponents must be equal. So 5x must equal 4x minus 2. Okay, and we can solve that for x. Just subtract 4x from both sides. X is going to end up equaling negative 2. Okay, so that one you just had to use a little extra step there and remember those properties of exponents. Okay, how about one more? 2 to the 2x plus 3 equals 1/8. All right, so with this one, again, the side with the base is a base of 2. So we got to see, is there a way for us to write 1/8 so that it has a base of 2? And hopefully we remember, or we can kind of think about 2 to the third equals 8. Okay, so this problem is really 1 over 2 to the third. And the way you get the 2 to the third in the denominator is if it were a negative exponent. So remember 2 to the negative third would end up becoming 1 over 2 to the third, which in turn becomes 1/8. So the 1/8 is really equal to 2 to the negative third. And we were able to write both sides with the same base now. So now I can just set their exponents equal to each other. 2x plus 3 has to equal negative 3. And we can just solve this like a normal linear equation. 2x equals negative 6. And when we divide by 2, we get our answer of x equals negative 3. Okay, so just watch out for that. Again, anytime you see fractions or reciprocals, that's where negative exponents come into play. All right, could we do something like this, though? Could we do 2 to the 2x equals 9? So is there a way to kind of rewrite 9 as 2 to some power? Okay, and there probably is. It's just not a nice whole number, right? There's certainly 2 to some power would equal 9, but it's not going to be a nice number. Okay, so to solve that, we really can't use the method that we just did. What we're going to have to do is use some other techniques, which we're going to kind of introduce right now. It's going to use logarithms. Okay, so logarithms are really designed to help solve exponential equations, and they have some of their own uses as well. But one of the big uses at this level is going to be to help us solve exponential equations. We will see logarithms are actually the inverse of exponentials. Okay, and they're going to have some uses, like I said. So let's look at how those work, a little introduction on those, and then we'll come back later on and figure out how to solve equations using them. Okay, one of the biggest things to understand here is how to convert, like if I give you an expression like an exponential, or an equation I should say, how do we convert that or rewrite that into log form? Because you're going to need to have to go back and forth sometimes. And then kind of get into a calculator to actually solve some things. But there is a way to do this. So if you take a look, if there's any exponential form on the left here, right? It's b, I used b for base, right? So some base to the y power equals x. I'm just looking right here. Okay, that can be written equivalently in log form, logarithm, okay? And log is the abbreviation for that. When you write something in log form, you're going to put a base. Okay, so that lowercase b is actually like, it's a subscript. It's written lower and kind of smaller. This right here is not b to the x power. The x is kind of in line with the log, and the b, again, is a subscript written lower. So just make sure you're clear on that. And it equals y. So if you notice what happened, the base ends up becoming the base down here. But again, it's not raised to the x power on this side. Over here, this would be read as log base b of x equals y. Okay, so I just want to make sure we're clear on that. The exponent in the exponential form ends up being what the log equals. And then what the exponential equals, sorry, all this highlighting looks the same color, but I did color code the letters at least. What the exponential equals is the number you're taking the log of. Okay, so let's look at some examples. We'll throw some specifics together. So if you see an exponential equation like 5 to the third equals 125, okay, that's just a true statement, right? 5 to the third power does equal 125. If we want to rewrite that, it's going to be written this way. So the log base is the same as the base that you're raising to a power of 125, and logs always equal the exponent. Okay, say it again, the log always equals the exponent. That's really what logs are. Logs are exponents. Okay, and what's going to end up happening, eventually, one of these three values, either the 5 or the 125 or the 3, will be unknown, and we're going to have to do some work to find it. Okay, for now, we're just changing forms on it. Okay, let's do the other direction. Can we write, if I give you a logarithm, can we write it in exponential form? Okay, so log base 3 of 9 equals 2. Okay, so the base is the 3. Remember what a log actually equals is the exponent. Okay, and then 9 is the number we were taking the log of. And 3 to the second power does equal 9. So these are just true statements, and we're just kind of rewriting them. Okay, similarly over here in part B, the base, log base 10. Okay, to the negative second power equals 1 over 100. And again, true statement. It's just a statement. We're just practicing changing forms right now. Okay, so knowing how to convert back and forth will become useful. In the next section, we're going to look at solving some equations, and then eventually there's properties of logs where you'll have multiple logs and you need to kind of simplify and things like that before you actually go and solve an equation. But at this point, just make sure you're comfortable on going back and forth, and then earlier in the section, also able to solve equations by writing both sides to have the same base. All right.